this sum is just a mathematical problem. You are adding 1 squared, 2 squared, all the way to n squared. So it's math. This is physics. We don't care about math. All we do is to grab your local mathematician and ask them what is the sum of this. And then they will tell you that this sum will equal to n times n plus 1 times 2n plus 1 divided by 6. You don't need to know this. You don't need to memorize this. You don't need to worry about it. It's not going to be on your exam or homework, but because we are doing scientific irrigation, so we need to let's make it exact and actually do the calculation. You look at this formula as a physicist or as an agriculture student, you don't know how to get it, but you do know how to add numbers and do multiplication, so you can check it. The way you check it is to just plug in numbers. So let's say I'm just adding 1, which equals 1. And according to the formula, you should get 1 times, what is 1 plus 1? Good. And what is 2, 1 plus 1?
3.
Good. So you get 1 times 2 times 3 divided by 6, and that is
1.
good. So, okay, your formula makes sense for n equals 1. I'm going to try it again for n equals 2. So 1 squared plus 2 squared is 1 squared plus 4. 2 squared is 4, right? 2 times 2 is 4. So 1 plus 4 equals 5. And let's use the formula. 2 times 2 plus 1 is 3. And what will be 2 times 2 plus 1? Good. So you see the 6 get divided by 2 times 3 is 6. And you get 5. And your formula makes sense. Okay, so as a environmental science major, let's just call it a day and say, all right, your formula worked. I trust you. Okay. Now, because we are going to cut the rod into many segments, so we can treat each small segment as a particle. So n is really big. If n is really big, n is basically just n plus 1 is still n. It doesn't matter how, like $1 million plus $1 is still $1 million. So n plus 1 can be approximated as n. What will 2n plus 1 approximately be?
2n.
Good, 2n. You cannot drop the 2 because 2 million plus 1 is 2 million, is not 1 million. You can drop the plus 1, but you have to keep the twice in front of them. So 2, 6 cancels, you get n cubed divided by 3. Okay? It's just a math question. You don't need to know how to do it, but we're doing it for fun. So now, when you come to here, lambda is lambda, L squared gives you L cubed, n squared gives you n cubed, and we just get that this sum is n cubed divided by 3. So you see that n cubed and n cubed cancel. It doesn't matter how many sigma you cut the rod into, it gives you the same answer. The moment of inertia for this rod is 1/3 lambda L cubed. Okay? So that's how we get the moment of inertia for a macroscopic object. You cut it into many small segments and add the moment of inertia altogether. And what we are doing is we run into some mathematical problem, usually a sum of a lot of terms, but it's just math. All it gives you is this extra factor of 1/3. And this factor comes from this sum, and we are doing this sum because the shape of the rod is linear. If you are doing something with different shape, you will cut it into different, you will cut it in a different way, and you are going to deal with different type of sum, but at the end, you just get a number. The physics is in the dimension. We learned that moment of inertia should be mass times distance squared. And the only thing affecting the moment of inertia is the linear mass density, the material of the pipe, and how long the pipe is. So what is the dimension of linear mass density?
Mass over length.
Good. So if you want to have something with mass times density squared, then you know your moment of inertia must be proportional to mass length over 1, and to add up to length to the power of 2, you need 3 lengths. So 2 lengths minus 1 length give you 3 lengths minus 1 length give you 2 lengths. So without doing any calculation, you know the moment of inertia of this rod is lambda L cubed. If you are good at math, you just get a 1 over 3, which is trivial, it doesn't have any physical meaning. And it just comes from the shape of the object. For example, if you have a disk, uniform disk, with radius r, and the mass is n, you know the moment of inertia is going to be proportional to mass times radius to the power of what? How many radius? Mass has dimension of mass. So should it be mass r, mr cubed, mr squared, or mr4, something like that? So here, lambda is mass over length because it is linear mass density. Here I'm looking at the mass of the disk itself. So without doing any calculation, which one do you think is going to be the moment of inertia? mr squared, good. Okay? So dimensional analysis, very useful. You don't need to do any calculation, you know it's going to be mr squared. And if you are good at math, you will get that there is a 1 over 2 in front, but that's just a math. The reason that this is 1 over 2 and this is 1 over 3 is because the shape is different. This is a rod, this is a disk. But there's no physics in there. The physics is in dimensional analysis. Okay? Alright, so finally we get this. We plug it into our time. The time we take is omega I divided by LM. So I is 1/3 lambda cubed L cubed divided, so cube minus 1 gives you square. So you get omega lambda 3f L squared proportional to L squared. So if you want your pipe to be 2 times longer, the time it takes to reach that desired angular velocity will be 4 times longer because it is L squared. Okay? Okay? Alright, let's watch some video. Okay, video. Our final topic for today is angular momentum conservation. It is the last conserved quantity you learn in this class. And it's a lot of fun.
Flexibility, control, centering, speed, and her signature trademark field of spin.
Brian was ice skating. This is Dennis Bellman. So what you saw is that when she get her body closer, she can spin faster. I don't know how to ice skate, but I have this tool that can spin. So have you guys seen this before? Someone? So initially, when she's spinning, she have her arm open, and then she bring her body close, and then you can open again. When you bring your body close, your angular velocity increase. But when you release it, it decreases again. So you can increase again, do some spinning, go down again, right? So that's angular momentum conservation. The conserved quantity, angular momentum, is related to what you learned today by I omega. It is the moment of inertia times the angular velocity. And it is conserved if there's no torque acting on the stool. So the reason I can do that is because this tool can spin freely. There's no friction. There's no torque stopping it from spinning. If I apply a torque, it will stop, and angular momentum will flow out of the system. But angular momentum will be conserved if there's no external torque acting on the system. Okay? Now, the difference between momentum conservation is that the inertia is moment of inertia. When the distance of the mass is closer to the center, r is smaller. When r is smaller, what will happen to I? When you bring the thing closer, is it easier to rotate or harder to rotate?
Harder.
So if I initiate it like this. Yeah. You guys can try it later if you want. Moment of inertia is mass times radius squared for all of them. It might be complicated to actually compute it, but you know if you bring the mass closer to the center, then the r is basically decreasing. And if r decreases,